Right, so I think we're going to stare at this thing for a while, and then possibly add some more features using AI. But anyway, yeah, so we're gonna like talk through this though. I'm going to first go to a lower dimension because you know there's it's like a pretty weird bird outside my window. Alright. So yeah, we're just gonna. This is like a neural net visualizer, and going to talk through it, cause cause like ultimately we want to use the goal here is we're gonna have this kind of visualization, and then we're going to see if we can like use it to like program a neural net, right? And like, is that a stupid goal? Quite possibly. But alright, so I'm gonna talk through this stuff, right? Like, this is so yeah, so right. So this is a neural net that's on two inputs. So there's like four 2 power 2. There's like 4 possible inputs. It's like 0 0 0 1 1 0 1 1, right? And so what all of these rows are visualizing is like pairwise distance betwixt. So it's saying like this entry is the distance between the Hamming distance between 1 0 and 0 1, which Hamming happen. I was gonna do like anyway. It happens to be 2, and because we're in dimension 2, that's like the maximal Hamming distance. So like it's bright yellow, right? So like you have this diagonal, like these are all the points and their negations. And yeah, and then like black is 0 Hamming distance, so on and so forth. We then have a neural net or we have like a layer that maps, as like neural net layers do, it maps each two-dimensional input to like a different two-dimensional input. And it would probably be better if I had like if I had like a visualization for that. So we might add that. We might add that as a feature later. It's like it's like any feature requires so many like blood glucose. Anyway, so in this new representation, like we can say like in the new representation, like this top row here, it's what 0 0 is being mapped to, but like we don't have, it's not necessarily 0 0. But either way, what it's saying is that it's saying that it has become farther away, like from this input in the new representation, right? Like, yeah, like the uh, the new representations retain their labeling of like the input that it's associated with, right? So anyway, like this input, it got farther away, like it bumped up a distance from this guy, stayed the same with this guy, and got closer to this guy. And so that's what's, yeah, that's what's being visualized in this row. So like the red is you have increased distance relative to the inputs, and the blue as you have reduced distance relative to the inputs, and the white is no change. Yeah, so, okay, so like we'll do one more layer here, right? Like this layer goes to here. You know, so like this particular point, it goes from being maximally distant to being zero distance. So that's a blue. And oh yeah, anyway, like these are relative to the start, not per layer. So it's just saying, like, if you look at these distances relative to here, you know, like these two are identical, these two are smaller, and yeah, like these two are smaller, and so forth. Yeah, I mean, it's, you know, like we're kind of hoping like some cool patterns would emerge, but that's probably not going to happen. But no, like the overall goal is it's going to be this app, except we're going to have like a target function, and then we're going to select layers based on, you know, like if it looks good. Yeah. Okay. So let me just focus on this bottom layer. So, right. Yeah. The bottom. Well, I mean, it's not. It's the bottom row. Like these are not. The rows do not correspond to neural net layers. The columns on the visualization correspond to neural net layers. Okay, so like the bottom row is how much each layer improves with respect to the final output. So here, like the final output, like there's actually things here. It's just that they're all black, because what this neural net is doing is it's mapping all of the points to a single point. And so this is just saying that, you know, like the Hamming distance between a point and itself is 0. So if you go to this layer, and we treat that as like the target output, right? Like, yeah, I mean, like that's what we're going to do. We're gonna have like a target, you know, pattern here. It just happens to be, in this case, it's all black. Yeah, it would probably be, actually, let's just reduce the layers. I mean, you know, like it seems like the general pattern, it kind of seems like, you know, like if you run these things long enough, all the points will be mapped to a single point. I think it was basically because that's irreversible. So, yeah. There's probably some, yeah. It's some sort of, you know, I mean, it's basically like a random walk except like every point is doing a random walk, except like they're correlated because every step has to be implementable as a single layer in a neural net, which is like a pretty severe constraint, although it's hard to comprehend. Anyway, we're just gonna go. We're gonna reduce the number of layers here. That's cool. Okay, and then we want to get a target output that is not a single point. Okay, gonna need to reduce it some more. That's fine. All right, here we go. Like now we're getting some good stuff here. So we can interpret this as like, like the target output, like basically what it's, yeah, I mean basically what it's saying is it's separating this one input. So like this one input is distance 1, like in the final representation, it's distance 1 from every other input. And also all of the other inputs are at a single point. So what this neural net is doing is it's taking the 4 inputs and it's collapsing 3 of them to a single point, and then it's keeping the other point separate. And I mean, even geometrically, it's like this distance is 1, so like like you can visualize the thing as like it's it's like a square, and like we're mapping 3 of the corners of the square onto 1 point, and yeah, actually, like it's this first layer. What's happening with the first layer? So like the first layer, I think, is just collapsing. It's, yeah, okay, so like the first layer is collapsing 0, 0 and 1, 1, while I think keeping everything else the same, right? I mean, like that's what this delta is showing. And like that's irreversible because they're being collapsed to the same point. And then it's is it like doing, I don't know what it's, I think it's just bumping. Yeah, that's fine, that doesn't matter. Yeah, I mean that's kind of one of the good thing with like pairwise symmetry, or like no, pairwise distance representation, because it's yeah, like the actual I think it's yeah, like it's stable to like rotations of a hypercube. Yeah, because there's like a lot of rotations of a hypercube. There's n factorial 2 power n, so irregardlessly, okay, so we want to focus on this layer. So what this layer is saying is that, right, so we're treating this as like, like we're starting here, and we want to be here, or, I mean, like here, right, because it doesn't change once you hit that. And, I mean, eventually this is going to be like, like as humans, we're going to try to implement this. I mean, this is basically a waste of time, but that's fine. So, right, and so what's going to happen is what this row is saying is, it's blue, like if that pair has improved right, so like currently, like if we're starting here, this pair are like maximally distant from each other. And we want them to be 0 distance from each other. And so in the first layer, we achieve that. Like we go from like distance of 2 to distance of 0. And so down here, it's like blue if that's a good thing. Yeah, so like that's a blue. So it's kind of the idea of like, if you were trying to pick like which layer, like this would be a good layer to pick because it's all blue. Like they all improve. Like all of the pairs improve. Relative to like the desired output. And right, so then the next layer, right, so when we go from this layer to this layer, right, so, well, like what this is saying is that we're just improving this row and column. Which basically means like we're just moving a single point. And I guess like if you look at this, like that is what is, it's saying like this, these are already set, which is true. And like this column is already set except for that row. This column is set except for that column. Yeah. So that's what's happening. Like it's, yeah. Okay. So with that idea in mind, let's go to like a higher dimension. I'm going to go to like a higher dimension, and then and I think we'll just like, I mean, I don't know if I have fully. It's not quite clear how to implement this because it's going to be like you're starting here, you want to go here, and we're gonna have a thing that like visualizes like random layers, and right. So I mean, there's like a lot of layers that you can have for here, and this little visualization is telling you like, hey, the red pairs are like bad. So like the first layer here is actually introducing, is making things worse on these pairs. Like for instance, if we look at this pair, it's supposed to be black, but it goes from like distance 1 to 2. So that's saying you have unimproved that entry by 1. But then of course in the next layer, it fixes everything, I guess. Right, yeah, I mean, like if you look at this entry is being improved by both layers. Yeah, I mean, it's basically combinatorially impossible to but that's what I want to implement, is this idea of like, we're starting here, we want to go here. Give me a bunch of like random because I mean, heuristically, you wouldn't even think of like using this, because you're only improving on 4. Also, there's I think like, well, yeah. Um, anyway, yeah, it's like you wouldn't, like a human wouldn't really select this layer, because it's like you're messing up, all of the reds are like you're unimproving those pairs. Um, I mean, if you look at it from the perspective of a single input, it's saying like, if you just look at the second row, like the final out, oh dang, man. I don't have mouse panning. There we go. The second row is saying like, you're supposed to be identical to this block and this guy. And then you're supposed to be maximally distant from like all of those other guys. And I'm gonna say like the first layer, it's yeah, like you're supposed to be close, so but it's like moving you away from this guy, and yeah, I mean it's messing you, like it's moving you away from 4 points, or it's moving you in the opposite direction of fully half of the input space, whereas on the other points it's either no change or it's helpful. So it's only helpful like on 2 thingies. It just so happens, I guess, that once you're in the representation being produced here, you'll have like this representation. And alright, let's go. Let's do a higher dimension again. 6. Dang, man. Yeah. Right. So, right, I mean, like, if you look at the first layer, like, you have a ton of reds, right? Like, every red is saying that that pair of points are being moved, like, farther apart when they're supposed to be closer, or they're being moved closer when they're supposed to be farther apart. They're being moved erroneously. Right, and like this layer, everything is red on this layer. And then it's kind of like, I guess you kind of get more, I mean, I don't know if there's more blue, like maybe you should just, sum. It's only in the final layer that like everything is corrected. Right? I mean, like the final layer has to make like all of these corrections. And that is completely non-interpretable. So yeah, but I mean, like I'm still gonna make this thing. I'm still gonna make my app. But yeah. More layers. Right. So, and like, yeah, like I think in this case, like this is the final layer. Right, we've mapped all points to these 2 points. Right, I mean, like if 2 rows and a Hamming distance pairwise thingy, if 2 rows are identical, that implies... No, I don't think that implies they have to be the same point. Well, no, it does. Yeah, no, it implies it, yeah. Because... yeah. Okay. Anywho, dang. If we look at the like the progress layer, you know, first layer, a lot of progress, a lot of lack of progress. Weird ovals. We got some ovals happening. That's pretty cool. You know, then like this thing happens. Then you have these big chunks and like more stuff. And then you know, like this layer seems to be mostly like bad. And then this layer does nothing. And then you get like two layers that are corrective. Okay, that's cool. Okay, yeah. We're gonna keep in like lower dimensions because higher dimensions are bad. Um. Yeah. Okay, so all we have to do is implement like a cool user interface. It's like you're gonna start here, which is the natural pairwise distance matrix, and then you're gonna have like some arbitrary pairwise, target distance matrix that you're trying to achieve. And then like what's gonna happen, I think, is like it's something like you're going to you're just gonna like generate random layers, and like that layer will be displayed like using this. So like just telling you on each pair of inputs, are you like the pairs that have to be closer together, are they getting closer together? The pairs that have to be further apart, are they getting further apart? Right. So like if it's a good motion in that sense, then you get like a blue color, and if it's a bad motion, you get a red color. And but the idea that like if the human is picking the specific parameterization based on, it seems kind of like you would have like maybe like a tree. The problem with that is like trees are very hard to just like, well, yeah, I mean, it'd be something like, okay, like you'd start here, okay, and then it would just generate like a bunch of random possible layers. they're just given by this like improvement unimprovement display. And then I don't know, like you'd click on one and it would select that, and then and then it would, now that you have like this new representation, like it generates next possible layers, and and um yeah, and then you just do that. That seems highly complicated to from like a user interface perspective. Like clicking on things and then having like trees come out. That's pretty hard. Well, I mean, I think like you can yeah, we can have it like because these are all like it's easy to do a click detection on those, I think, because they're just single geometries. Yeah, I want to do that. Yeah. Right. You'd have like this thing on the top, like this was like your target representation. This is your current representation. I think this one is displaying the this one is displaying the errors with respect to the target. And yeah, so that was kind of the thing. Because I guess basically, I mean, like the heuristic is just oh, well, yeah, but you'd be looking here, actually. Right, yeah. Like the heuristic is just kind of, the correlation between these two, I think. Because, like, this is the, like, starting representation right here, this guy. I mean, it's literally this matrix minus this matrix, or possibly the other way. But I mean, it's saying like, I mean, like, you know, this chunk here is all black, whereas here they're higher. And so here it's saying like, you know, this little sub-square at the start, all of these points are too far, too distant from each other with respect to the target, because they're supposed to be identical or zero distance. So that's reflected here by saying like these are all red. And then the first layer kind of correlates with that, kind of. I mean, that's the heuristic. Like, you want this, you know, like wherever you have reds over here, you want, let's see, do you want a blue? Yeah. Yeah, I mean, I think that's the original idea, is you're just like, okay, like, these are all too big. Yeah, I mean, I guess this is like reducing the error. I mean, you could just look at this visualization, because like this one is getting. I mean, if it's like a white square is like correct, like those two pairs are. Yeah. Actually, it'd probably be better to not have user. It'd probably be better to not have clicking. Possibly it'd be better just to have, you know, this and this, and then you're just like, you're gonna animate, like, just random search, I guess, here. And then, I don't know, like, you just pick the layer with the most, like the least erroneous layer, and then you just iterate. Yeah, or I mean, like, you could do a thing like where, like, because here we have like an actual solution, because it's just a random neural net, and then we're just treating this as the target we were trying to achieve, even though we were not. But yeah, you could then say like, well, how easy is it, given this, you know, given like an actual solution, how easy is it to like recover like this, I mean, like, not this specific solution, but any solution. Yeah. All right, yeah. So I think I hit my burned all my blood brain glucose. So because that was what, like 40 minutes. Yeah, yeah, yeah. I mean that's okay. I'll do the other 20. You know, you gotta get your full hour of JavaScript. Um, trying to yeah, maybe like the easiest way of doing it, like maybe a cool thing to do, probably not, would just be, yeah, like you do this, which we've already done, you know, and then like you just animate, I guess, trying to um, replicate the do, do, do. Yeah, I mean, yeah, yeah,